Hello everyone. Today we will be discussing the eighth practice problem, which is Leetcode problem 72, edit distance. So this problem is actually a very famous DP problem and it is asked in a lot of interviews and tests. So let's go through the problem statement first. It states that given two strings, word 1 and word 2, return the minimum number of operations required to convert word 1 to word 2. You have the following three operations permitted on a word: insert a character, delete a character, or replace a character. So let's try to understand this question using an example. Let's say that we have two strings. So word 1 is string WXH and word 2 is the string ABH. So when we start with the original strings, we first see that whether the characters match or not. Since the characters do not match, we have three options available to us. The first option is that we delete the character in word 1. If we delete the character in word 1, we will be left with these two strings. The second option is that we replace the letter in word 1 with the letter which is there in word 2. So if we replace the letter W with letter A, then A and A will match and the remaining strings will be XH and BH. And the third operation is that we insert a letter. So if we insert a letter A in our first string, so if we insert the letter A and A will match. So we will be left with string WXH because we have added a letter A which has already matched in it, and the other string which will be left will be BH because A in this has already matched with the A that we inserted. Now further in this string X and A do not match, so again we have three options. We can either delete X and then we will be left with H in the first string and ABH. The second option is that we replace X with A, so A and A will match and we will be left with H and BH. And the third option is that we insert a letter A in the first string. If we insert the letter A, then XH will be left in the first string and the A of second string will get matched and we will be left with BH in the second string. So again, all the other branches will be expanded in a similar way. Let's try to expand this branch. So in this, the first option is that we delete X, so we'll be left with H and BH. Second is replace X with B, so we'll be left with H and H. And then our third option is that we insert a letter B, so we'll be left with XH and H. Now in this particular case, H and H will match, so we don't have to do anything and we'll just move forward. So since H and H will match, we'll be left with two empty strings. And since we are left with two empty strings, we do not have to do anything else. So here we can easily see that this is forming a recursion tree and it can be solved using recursion because every step we are making three recursive calls. So in the three recursive calls are representing the three operations, which is deletion or replacement or insertion of a letter. Now if each recursive call returns the minimum number of operations of making these strings equal, we just have to choose the minimum out of these three, and whatever is the minimum out of these three will be the answer for this step plus one for the operation that we have performed. So we can solve it recursively, and using the intuition of recursion we can pass the sub problem to be solved by the recursive method. We don't have to worry about it. Recursive method will return the answer and then we'll solve for the current case. So let's go through the recursive solution. So this helper method is basically going to return the minimum number of operations to make these two strings equal. And I and j are basically representing the index of the characters that are being compared right now. So when the letters I and j have matched, so we have already discussed, in that case we do not have to do anything since the letters have matched. So we will start comparing the strings from both the strings from the next letter. But in the case when the letters do not match, then we have three options. So in the first option we are doing a I plus 1. That is because we are deleting a letter but we are not touching j. In the second recursive call, what we are doing a j plus 1, we are not touching I. So this is case representing insertion because we are inserting a letter in the first word. So the letter in the second word and that inserted letter will match. So we do a j plus 1 for the second word. This was a case of deletion. And in the third case, we are doing a I plus 1, j plus 1. This was the case when we replaced the letter in the first string and that letter became equal to the letter of the second word. So now we'll start comparing from the next letter of both these strings. So out of these three operations, whichever operation is going to return the minimum number of steps, that we are going to pick for this step. And we are also doing a plus one because we have performed one operation, so we need to add the cost of that operation. So whatever is returned for the remaining strings, minimum returned for the remaining strings plus one for this step, is going to be the answer, final answer for this step, and we have simply returned that answer. Now the base case is also pretty simple. The base case is when the size of either of the two strings becomes 0. So when the size of either of the two strings becomes 0, we can simply return the answer from here. Because if the second string has become of size 0 and we have still words left in our first string, in that case, the only option is to delete all these letters. So the cost will be basically 1 into size of the remaining string because we need to delete all the letters. And the second case is when string 1 becomes empty but there are still letters in the second string. In that case, the only option is to add all these letters into string. And inserting all these letters in string 1 is going to take a cost of 1 into the length of the remaining string. So in both the cases, we can simply return the total number of operations for making these strings equal. So this is going to act as our base case. Now this recursive solution runs into time limit exceeded error. So we can see the reason easily in our recursive tree. So in our recursion tree, we can see that this particular problem has been repeated here. So we will be calculating this problem again. And if we complete this tree, we will see that there will be many subproblems which will be calculated again and again. And that's why we can say that this particular solution has the problem of overlapping subproblems. And also it has optimal substructure because using the optimal answer for these subproblems, we can find the optimal answer for our main problem. So since it has overlapping subproblem and optimal substructure, we can use DP to solve this question. And the first obvious optimization would be memoization. So the memoization implementation, as always, is very similar to our recursive code. So we have just declared a map. This map is going to store the answer for a subproblem. So subproblem is represented by the two indices, the indices which we are exploring right now. So if we have solved a subproblem, we will store the answer for that subproblem so that we don't recursively solve it. So the main logic is similar to the recursion logic, but in this the extra step is that before leaving or before returning the answer, we store the answer for this subproblem in our map. We make an entry so that we do not have to solve this subproblem again. And the base case is also similar. The other step is that before solving a problem, we check if we have already solved this subproblem. So we are seeing if we already have an entry for this subproblem in our map. If we already have an entry for this subproblem in our map, then we simply return the value stored against this in the map. We do not solve it recursively. If we have not seen this subproblem earlier, we'll solve it recursively. So this is how memoization code works here. So the recurrence relation for this problem. So let's say that f is the function which is going to return the minimum number of operations to make these strings equal. So f of ij is going to be equal to f of I plus 1, j plus 1 if str1i is equal to str2j. So if the letters match, then we simply start exploring the next indices in both the string. Otherwise, our answer will be equal to 1 plus minimum of I plus 1 j, I j plus 1 or I plus 1 comma j plus 1. So these three are representing the three possible operations, and we are taking the minimum out of these three operations, and we are just adding the cost of this operation. Now from the recurrence relation, we can easily see that this problem can be modeled as a 2D matrix. So we'll also try to solve it using tabulation. So first of all, we have declared our helper matrix, and the size of this helper matrix is m plus 1 into n plus 1. So m here represents the length of word 2 and n represents the length of word 1. So rows are going to represent word 2 and columns are representing word 1. In rows and columns, the first row and the first column are actually representing the empty states. So the first row represents the empty state of word 2 and column represents the empty state of word 1. So as we discussed in our recursive solution, we are using these empty states as the base case because when either of the string becomes empty, we know the exact number of operations required to make the second string equal to the first string. So first of all, we are filling up our base cases. So in the first row, we are assuming that word 2 is empty. So when word 2 is empty, so the total number of operations required to make word 1 equal to word 2 will be equal to the length of word 1. So when length of word 1 is 1, the operation will be 1. When it is 2, the operations will be 2. So similarly, we'll just filling up that row. And for the column, word 1 is empty. So again, the operations required will be equal to the length of the remaining string. So we are simply filling the first column. So now we come to our main logic. So in this particular solution, we are actually doing a little reverse than what we were doing in recursion. So let's say that we have two strings ABC and HFC. So when we are comparing these two letters, if these two letters match, then we don't have to do anything. So the minimum operations or the minimum cost of making these two strings equal is essentially equal to the cost of making these two strings equal. So that is what we are doing here. If the letters in these strings represented by I and J match, then the cost of making these strings equal is equal to the cost of making the remaining strings equal, which is I minus 1 and J minus 1. In case if these two characters don't match, so in case if it is ABE and HFZ, so these two characters do not match. So in that case, we have three options. We can either replace Z with E. So in that case, we would have to find the cost for the remaining string. One case is that we insert Z here. So in that case, we would have to find the cost for ABE and HF because these Z will match with this Z, so the remaining string will be these string. And the third case is that we delete E. So if we delete E, then we would have to find the remaining cost for AB and HFZ since these are the remaining strings. So these are the three cases being represented here, and we are trying to find the minimum of these three cases and then adding one for the cost of the operation that we are going to perform here. So in this way, we are going to fill up our entire matrix bottom up, and finally, whatever value is present in the bottom rightmost corner, that is going to store the final value of making the entire strings equal. So we are just returning that value as the final answer. So let's talk about the time complexity. So for memoization, let's take an example. So we had strings ABC and XYZ. So for these two strings, what are the different subproblems that we would have to solve? So for these two strings, the different subproblems that we would have to solve would be ABC, XYZ, BC, XYZ, C, XYZ, then ABC, YZ, then BC, YZ, and then CYZ, and lastly ABCZ, BCZ, and CZ. So these are the different subproblems that we have to solve. And as you can see, the different subproblems, the total different subproblems we would have to solve are going to be m into n, where m is going to be the size of the string 1 and n is going to be size of string 2. So there are total m into n subproblems that we would have to solve, and we will be solving each subproblem once. So the final time complexity for memoization solution is going to be m into n. And for the tabulation solution, it is pretty simple. So we are using a helper matrix. So space complexity is also m into n. And since we are filling the entire matrix 1, so that's why the time complexity for that solution is also big O of m into n. So with this, I think we can end this video here. In case if you have any doubts, as always mention in the comment section, and I'll see you in the next video. Thanks for watching. Bye bye.